Okay. Shall we start?
Yes, please.
Hello, everyone. This is the first session of today. My name is Dong Yang, and I'm the chair of this session. This session includes 4 talks. The 4th talk is given by Ludovico, Lami, or exact solution for the quantum and private capacities of bosonic diffusing channels. Please.
Right. Thanks a lot, Dong, and thanks everyone for attending. Okay, so first of all, this is work done in collaboration with Mark Wilde at Cornell University now, although most of the work actually was carried out at LSU while I was visiting there. Okay, so right, so I guess states and channels I don't need to introduce to you. So, but of course, like the main quantum system of interest here is a single harmonic oscillator, which the Hilbert space is spanned by the Fock basis, right? So it's just the space of square integrable functions over R, but we can think of it as spanned by the Fock basis 0, 1, 2, and so on and so forth. And so that means that the density operator for us will be just an infinite matrix, okay, represented in Fock basis. And of course, okay, quantum channels model transformations undergone by quantum systems. So in the case of continuous variable systems, so a single bosonic mode, which is the system that we care about in this talk. This is of course relevant when you, for example, do quantum transmission of information across an optical fiber. Okay, so quantum communication of an optical fiber. So, for example, this bosonic mode could represent a mode of electromagnetic radiation. And so convenient representation for a quantum channel is, of course, the cross representation, which is something of this form, as in equation 3, which you have some cross operators that act from the left and right. Okay, so let's present our model, the channel we care about in this talk, which is the bosonic dephasing channel, which, as you see, it acts on, well, it's written in cross representation. In fact, it's a random unitary channel, right? It acts on a state by randomizing its phase. Okay, so by applying a random rotation in phase space, this is generated by this unitary operator that you see there. A dagger A is the photon number operator, the Fock number operator, and you apply a random phase distributed according to some probability distribution P over the interval minus pi. Okay, right. So this, of course, models, say, phase fluctuations in the optical fiber due, for example, to temperature variations or some path length imprecision, so uncertainty on the path length that actually, that light travels on. And the first thing to observe is that this NP is actually not a Gaussian channel, right? So, and that it's very much not Gaussian unless it's trivial, is the identity. And so, well, seemingly in contradiction with what I just said, but it's not in contradiction. The canonical example of a bosonic diffusing channels is when the probability distribution is what's called a wrapped Gaussian. Okay, so basically the angle phi is just a normal random variable, but this, of course, since it's distributed since a normal variable is distributed on the line, and here we have to wrap it around the circle, you get this funny formula that you see down there for the wrapped Gaussian. But this is basically just, it means that the phase phi is just a single Gaussian random variable. Okay. Okay, so this channel was introduced by Arcand, Memarzadeh, I think, and Mancini in 2020. And so the first thing to observe is that actually it behaves very well on the Fock basis. Okay, so for example, if you compute its action on the Fock state NN, and you just use the formula, and you remember that the Fock states are eigenvectors of the photon number operator, you get this formula here. So you see that the operator NN, ket bra NN, is actually an eigen operator of the channel. And so it gets multiplied by this coefficient, which I denote by dp and m. So I organize this coefficients into a matrix dp. And as you see, the action of the channel is basically that of doing the entry-wise multiplication of the infinite matrix that represents the input state by the infinite matrix TP. Okay, so entry-wise multiplication or Hadamard multiplication. And the important thing to observe here is also that TP, this matrix TP, is actually a Toeplitz matrix. Okay, so what does it mean? It means that the entry nm is just a function of the difference n minus n. Okay, so this means that, for example, all the elements on the diagonal are the same, and all the elements on the line above the diagonal are also the same, but possibly different from those on the main diagonal. And so, for example, one may be curious what this looks like for the wrapped Gaussian that we just saw. Turns out there's the matrix TP is also kind of as a Gaussian kind of the elements, the off-diagonal elements fall in a Gaussian way, right? So decay in a Gaussian way when you move outside of the main diagonal. Okay, good. So of course we want to use channels to send qubits, for example. So we want to put the quantum capacity, and I don't think I need to introduce that to you, right? So this is the scheme for the quantum capacity. So so you see, well, of course we want to send a system M by encoding it with an encoding map En, and then applying the channel n times in parallel, and then decoding the message. And we want the corresponding error that I denote by epsilon n to go to 0. Okay. And the number of qubits sent per channel used, this is called an achievable rate. And the supremum of all achievable rates that I, also denoted by R, unfortunately, as the reference system. Sorry about that. So, but the supremum of all achievable rates, that's called the quantum capacity of the channel. Okay. It's a very important quantity and very difficult to compute. And another thing that we may want to do with channels is to establish entanglement between sender and receiver. Okay, so this is there's another figure of merit for this task, which is the two-way assisted quantum capacity. Okay, so the picture is a little different in this case because you can basically apply the channel still n times, but the thing you apply it between, say, n, so that is Alice and Bob spatially separated. Of course, you're allowed to apply the channel n times, but between every application of the channel and the next, you're allowed to apply an LOCC, so a local operation and classical communication. And so after n uses, you're supposed to get a state which closely resembles a certain number of IBITs. Okay. And the two-way quantum capacity is, of course, the maximum number of IBITs per copy per use of the channel, that you get in the asymptotic limit with vanishing error. Okay, so there are also other figures of merit, for example, the private capacity or the two-way private capacity that are related to how much secret key you can generate, and also the strong converse exponents. Okay, so these are defined in just the same way, but you require the error in the transmission just to stay below 1 instead of going to 0. So it's a weaker requirement, so you get larger figures in principle, so larger quantities. So this Q dagger, for example, is a strong converse quantum capacity. This is in principle, it may be larger than the quantum capacity. Okay, and the problem, of course, we're going to tackle here is that of computing all of these capacitors for the Bosonic dephasing channel. And this problem was posed by Jiang and Chen in 2010, and also investigated by this paper that I mentioned before by Akan and Mancini, Memazadeh. And yeah, it's been open ever since. And the main result of this talk is that under a very mild condition on the probability or regularity condition on the probability distribution P, which is this equation phi, which means that basically one of its Renyi entropies has to be finite for some alpha 0 larger than 1. If that holds, which is the case in most practically interesting cases, you can compute all of these 8 capacitors. They all coincide, and they are given by this very simple formula in equation 6. Okay. Just log 2 pi minus the differential entropy of the probability density P. And okay, so in particular, this means also that even if you allow unlimited classical communication between sender and receiver, you still cannot do better than the quantum capacity. So the Q2, so the quantum capacity assisted by two-way communication, it's just the same as the quantum capacity. And also it tells us that generating secret key, the private capacity, is just as hard as generating entanglement. Okay, while in principle it could be easier. Okay, and the other thing to observe is that this formula here, this equation 6, the right-hand side of equation 6, is just the if you want to interpret it in information theoretic way, it's very simple. It's just the relative entropy distance between the probability distribution P and the uniform probability distribution on the interval, which is minus pi pi. Okay, good. So very simple formula. And it's also very easily generalizable to the multimode case. And I won't delve into this multimode case anymore because it's just really kind of the proof is really analogous, but I want to show you the formulas. So, well, this is the general channel. You have possibly correlated phases across many modes. And then you get an exact kind of the same formula, basically still the relative entropy distance between P and the uniform probability distribution, which now takes this form. And again, you have some finite Renyi entropy regularity condition. Okay, so, and this, it turns out that this is, so for finite dimension, the dephasing channel, it was known what its quantum capacity was, and it's indeed a formula which looks very much like this one, with the exception that you have a discrete entropy instead of the continuous entropy or the differential entropy. And this formula was found in this paper by Pirandola, Laurenza, Ottaviani, Banchi, 2017. And so you can, I mean, our formulas are kind of a generalization, but we will see the proofs are kind of a bit different. Well, quite a bit different because we're in infinite dimensions. So you have to be more careful, way more careful. Okay, so and the example for the wrapped Gaussian, very simple plot. That's the plot you get if you plug in this the formulas that I gave you for the case of the wrapped Gaussian. The case in which the phase phi is just a random, a normal random variable, basically. You can also derive, well, you can derive an exact expression in this case, but also approximate formulas that are very useful. For example, for gamma, which is kind of small, you get this universal dependence. Well, okay, yeah, exactly. 0.6 plus this log of 1 over gamma, basically, half of that bits per channel use. And when gamma is very large, you get an exponential decay of the quantum capacity, which also makes sense because, of course, when gamma is very large, the off-diagonal elements of the input state get very much depressed. So they get multiplied by a very small number. So you basically lose almost all coherence. So the quantum capacity and all capacities actually decay exponentially. This was already shown in this paper by Mancini and collaborators that I showed you. But here we find the actual formula. Okay, so they showed that there was some exponential decay. Okay, so some proof ideas. Okay, so let's keep things simple. Let's say that we want just to compute two quantities. So the quantum capacity unassisted and the two-way assisted quantum capacity, okay? Since, of course, the quantum capacity is always smaller or never larger, it's enough to prove a lower bound on a quantum capacity and an upper bound on a two-way quantum capacity. Okay, if you find that they're given by the same formula, then you're done. Okay, so A, lower bound. Well, the lower bound is very simple in principle, kind of. The idea is very simple because we just use the one-shot coherent information, okay? So one copy coherent information, that's enough. So that's the coherent information for those of you who are wondering. So it's a quantity that is very fundamental in computing the quantum capacity. And it's actually, its regularization coincides with the quantum capacity, as the Lloyd-Short-Devetak theorem tells us. And okay, so basically you have to plug a state. You construct basically a state on AA prime, and then you send the system A prime over the channel. And then you get a state AB, and then you compute this combination of entropies for that state. So to compute a lower bound on the supremum, you need an ansatz for the state psi, right? What ansatz do we make? Well, just the maximal entangled state over the first D Fock states, okay? Well, oh, sorry, K should start from 0 and then D minus 1, that's summation. And of course, the idea being that we want to make D tend to infinity, that we want a very large entangled state. Okay, so, but for now, let's keep D finite. Okay, so denoting by this TPD, the D times D upper left corner of the Stöplitz matrix that I introduced before. So you see immediately that the coherent information is given by this kind of entropic looking expression of this finite matrix. Okay, so if you want to go further and compute this trace, you could ask yourself, can I compute the eigenvalues of these operators, in particular of the operator TPD? Well, it's a matrix. In principle, of course, you can compute the eigenvalues numerically, but do we have analytic expressions when D is large? Well, in certain cases, yes, and it's very instructive to look at this case. For example, if the probability distribution P is supported onto set of angles that have this form, so you see kind of that are rationally dependent from pi. So if the probability distribution is just supported on just those angles, so you can actually see that this Toeplitz matrix is actually circular. Okay, so it has one further symmetry, so it's invariant under shift. So it commutes with the shift operator. Okay, the one that sends every vector of the canonical basis into the following vector cyclically. And so for circular matrices, it's very well known how to compute the eigenvalues because they're diagonalized in Fourier basis, and so discrete Fourier basis. And so in this way, you can actually compute the eigenvalues. It's very simple. You see immediately that they are actually given by this pk times d. Okay, so if that is the case, then you can easily compute this trace, and you get actually an expression which we very much like. And so now the problem is, can you somehow, so you see this is very special for just those probability distributions that have this kind of support condition. But when d goes to infinity, you can actually see that the set of angles becomes dense somehow. And so you expect that this condition becomes not so restrictive, right? Because you can simulate any probability distribution by, probability distributions of this form if d is sufficiently large, intuitively. Okay, so basically we want to generalize this discrete probability distribution to the continuous one. And how do we do this? Well, there's a theorem in asymptotic linear algebra called Zegos theorem that allows you to do just that. Okay, and applying this theorem is what requires us to use this regularity condition that I was describing before with the Renyi entropies. And by a swift application of the theorem, you can compute the limit of this expression when d goes to infinity, and you get exactly what you should get. Okay, so this is actually, so like for an arbitrary probability distribution P, this matrix here will not be circular, of course, right? So it will be just a Toeplitz matrix. So you can't apply this formula straight away, but you somehow want to apply it in the limit. Okay, and this is exactly what Zegos theorem tells you. This is it's a highly non-trivial statement in itself, but this is basically, I hope it makes sense why it should work intuitively, something like this at least. Okay, so far so good. What about the upper bound? Well, Q2 requires an optimization of a very complicated protocols. This, protocols intertwined with LOCCs. So, but the key observation is that this channel actually is what is called teleportation simulable, which means that using a channel is actually, so if I give you one use of the channel, to use it, whenever you want, this is exactly the same resource as a copy of the choice state of the channel. Okay. And see, the choice state is what you obtain by sending across the channel the maximum entangled state. And this equality works only in the limit when the maximum entangled state is sufficiently big. Okay, so basically what I mean is that whatever Alice and Bob can do on the left by having one use or multiple uses of the channel, they can do on the right. So having one choice state or multiple choice states of the channel. And the reason why this is non-trivial is that the choice state on the right-hand side is a static resource, while the use of the channel is a dynamic resource, right? So basically, on the right-hand side, you have already committed to the input of the channel. You say, okay, I don't care what the input will be. For now, I just send the maximum entangled state, and then everything will be fine. But in principle, these two things are not the same, because on the right-hand side, you committed to a state, while on the left-hand side, you're not committed to a state. You can send any state that you want. Okay, so in principle, the left-hand side, the use of the channel will be more powerful than the right-hand side. But for this special channel, for a family, wide family of channels, the two actually are the same. Okay, so teleportation simulability implies that the two-way quantum capacity is actually upper bounded by the distillable entanglement of the choice state in the limit. And so then you do some tricks, for example, upper bounding the distillable entanglement with the relative entropy of entanglement. Okay. That's a very well-known fact in entanglement theory. And then so you want to find yet another upper bound, which is, well, okay, since the relative entropy is defined as an infimum, I plug in an ansatz for the state and I get exactly this expression. It turns out if you plug in the right ansatz, And then you see, once again, Sego's theorem in the limit gives us the correct expression. Okay, so that basically concludes the proof. And well, it's remarkable that the Sego's theorem actually appears twice, one for the lower bound and one for the upper bound. Great. Okay, so conclusions. Right, we gave an exact formula for the capacity for all of these 8 capacities of the Bosonic dephasing channels, right? All of the private and quantum capacities, both both unassisted and two-way assisted, and also both strong converse and weak converse. And the formula generalizes a capacity formula for finite dimensional dephasing channels, right? But the proof is actually, it's way more delicate because it requires a lot of for example, Sego's theorem in asymptotic linear algebra, and also a bit of care with infinite dimensional systems. And where there are some open problems that I'd like to advertise. First of all, we don't understand the energy constraint capacities for this one. I would very much like to understand those. And also, there are related models of noise across optical fibers that are more difficult to investigate, and it would be really good to be able to say something more about these channels. For example, another very typical phenomenon is photon loss, of course, across an optical fiber. And for example, you get a more refined model of noise if you add photon loss to the picture. So not only dephasing, but also photon loss. And also for that one, we don't know how to compute the capacities. And with that, I'd like to thank you.
Thanks for the wonderful talk. And any questions or comments?
I have a question.
Okay, please.
Please.
Hey, Ludovico, nice talk. If this regularity condition is not satisfied, does that give rise to a channel where the capacities are separated?
We don't know. I just don't know how to do the computation, because you see, like this Sego's theorem, actually, if you use the original version, that's not good enough. You have to use some, so like people have put forth all sorts of refinements, right, for this theorem. So like basically there is a 50-year long research line on this, and like of course, like most of this is devoted to removing regularity conditions. So this was kind of the weakest regularity condition that we could find in this paper by Serra Capizzano, actually lots of Italian guys. So it's kind of the weakest regularity condition that we could find that guarantees that we can apply this theorem. Otherwise, we don't know. So it may be that the mathematicians have to work a little harder, or it may be that there is a separation, God knows. I would expect that in any reasonable case, there won't be separation, but
There would not be.
there would not be. Just while.
Okay. It's a strong conjecture, no?
Well, okay. I mean, I don't know. It would be surprising, right? I mean,
I don't know.
Like it's one of those things, like jumping on a plane that flies thanks to the difference between Lebesgue integration and Riemann integration. These kind of things don't pop up.
Okay.
Somebody said I would never fly on a plane that flies thanks to the difference between Lebesgue and Riemann integrations. So like, I mean, I would expect that regularity conditions don't play a major role here. It's kind of, but I don't know.
Okay.
Can I comment, Ludovico?
Please.
So we do have an alternate proof based on Golovkin-Stashevsky, right?
Right. That's right.
So perhaps the upper bound, we didn't include that in the paper, but I think the upper bound would still hold. Would we need the regularity condition for the upper bound to hold using that method? Because the regularity condition is for the Sego theorem, right?
Correct. Possibly not, but yeah, Golovkin and Stashevsky also, that's an infinite dimension. So at some point you have to yeah, okay.
The idea was that we can think of the upper bound as a comparison between the channel of interest and the channel that completely dephases, right? And
Correct. But how
uh,
do you compute the Golovkin-Stashevsky relativimetry between those
well,
two?
the point is that there's a data processing argument that underlying these channels are these distributions. And it's simply a comparison between P.
Oh, right. Yeah, exactly. Okay.
Uniform over 2 pi. Uniform over the interval minus pi to pi.
Yeah, now I remember,
So,
yes.
I think it would not be limited by that.
Yeah, I can't see right now exactly. Maybe I think you're right. Yeah.
But that's perhaps offline.
Mm.
Can I, quick question for your comment, Mark. Are you saying that in that case, all of the capacities would have the same upper bound again, and then therefore no separation? Is that?
I'm saying
The lower
they would
bound
have-
is not.
they would have the same upper bound, but maybe there would be something with the lower bound, because the lower bound still relies on the Zago theorem, and that requires the regularity condition.
I see. Yeah, thanks for the extensive answer. Interesting.
I have a question, and I'm wondering whether I'm not familiar with the continuous case, but just wondering whether the channel is the type of channel that just generate maximum correlated states.
This one, yeah, well, I mean, it's indeed, I'm like, if you send in a state which is, say, yeah, sure, kind of the choice state is maximally correlated. Let's put it like that, like this.
So it always create, since the entangled state, it always generate maximum correlated state, right?
So if the initial state is maximally correlated, then the final one is maximally correlated. Correct.
No, I mean, because you can define maximum correlated state independent of the ancillary system, right? Because you can freely rotate its basis such that the two bases are the same, right?
Sure, but if the initial state is not maximally correlated, the final one won't be maximally correlated in general.
Ah, okay. Okay, no. Okay,
But if the initial, it respects maximal correlation. So like if the initial state is maximally correlated, then the final is also maximally correlated.
Okay, because I mean, from the result, I can see that for maximum correlated state, the coherent information is always equal to the relative entropy of entanglement.
Correct. Correct.
Okay,
Yes. That's very much underlies what's going on here. Yes.
okay, thank you. Any other questions?
I have a question,
Oh, please.
and it's not strictly related to the presentation, but how many non-Gaussian, let's say physically motivated quantum channels are there for which we don't know the quantum capacity? Because this is my fault, but I thought that the phasing channel was a solved model in that sense. So how many others quantum channels in continuous variable non-Gaussian are there for which we don't know the quantum capacity?
Oof, well, okay. For example, this one that I wrote here on the slides.
Yeah, the loss. Okay.
Yeah, photon loss plus the dephasing, the one we don't know. Well, I mean, there are all sorts of families for like of channels that are Gaussian dilatable, so what they call Gaussian dilatable. So like, for example, sending a beam splitter, mixing the input signal in a beam splitter with a fixed state in the environment, which is not necessarily Gaussian. So this is also another kind of natural family of channels, but these are not like super important in applications. I can think of many others.
Your co-author today stressed how important that model is in applications,
Yeah, okay.
right? Sorry.
So which model?
Where you're like changing. the environment.
Sure. Right.
Yeah.
No. Okay. Of course. Right. I mean, for some crazy states, crazy environment states, this is not, yeah, I mean, like, it's not, of course, like if you engineer it, that's another story. But if you want just to state that a channel that you find naturally in the environment, that's gonna be Gaussian most likely. I mean, unless it's a very short fiber or a very active environment somehow where active optical components do something, or you engineer it to be this way. Yes.
Okay, thank you.
You're welcome.
Any other questions or comments? If no, let's thank Ludovico again. Thank you.
Thanks a lot, guys.
Okay, you can turn off the CRI.
Are we doing the breaks or are we just going right into?
We should probably go right into it because of the delay, right?
Okay,
I'm fine with that. Yeah.
Right.
Should I start sharing?
So Felix, you are the speaker, right?
Yes.
Yes, please proceed the next talk.
Ah,